Good afternoon. My name is Keith Hare. I'd like to spend a few minutes this afternoon looking at an example of replicating an RDB database to Oracle 23AI. The tool that we're going to use to do this replication is something that we call the JCC LogMiner Loader. It allows you to configure replication of committed transactions from an Oracle Rdb database to a variety of targets. And this example, for the target, we're going to use Oracle 23AI. And we'll also spend a few minutes talking about some of the interesting property graph capabilities in 23AI. So, going to spend a few minutes on a number of topics. Explain how the LogMiner Loader works, go through the details of an example, and then take a look at property graph queries. The JCC LogMiner Loader uses the RMU unload/after utility to extract committed transactions from the RDB database. It then applies those to a target someplace. And the resulting replication is close to real time, but more importantly, it is transactionally consistent between the source database and the replicated target database. You would do this replication because you want to take your production database, production data, and put it someplace where you can do additional reporting, ad hoc queries, support a website, etc., without interfering with the performance of the production application. So the source for this replication has to be an Oracle Rdb database. Any version that supports the LogMiner, the RMU unload/after command. The target is can be a variety of things. There are database targets such as Oracle Rdb, Oracle using the SQLnet client, or a JDBC Class 4 driver. We also support replicating to a number of intermediate targets such as Tuxedo, XML with your own API, a file, or publishing to Kafka. The format of the target database can be completely different from the format of the source database, both logically and physically. We'll talk a little bit about what the issues are and the things that you can tweak. The tuning can be different. You need some indices to support the queries from the replication, but the placement, the buffering, caching, all those physical performance capabilities can be different on the target database from the source database. So the big picture is you've got an RDB production database that we'll call the source. You have after image journaling enabled to support the transaction logs. You have some sort of workload that updates the source database. You may have AIJ backup journals. We have an options file that tells the RMU unload/after command to the continuous log miner what data to unload. We point the RMU unload/after command at an open VMS mailbox, then read from that mailbox based on the criteria that you configure, and we apply it to whatever the target is. And there's a number of files that have to be set up to do the configuration. But the thing to note on this is that the blue items are part of RDB. The green items are the JCC LogMiner Loader. In this example, we're going to use a source database in RDB using version 7.4-120, so a recent version. We're running on OpenVMS on Itanium with pretty much the latest OpenVMS version on Itanium. running this on an HP integrity. Actually, in this case, a BL860C with 16 CPUs and 80 gigabytes of memory, and we're using a recent Java version. For the target database, built an Oracle Linux 9.5 server and installed Oracle 23 AI Free. This is a virtual server, so the virtual x86 server with 2 CPUs and 32 gigabytes of memory. So the source database, we need to be running RDB version 7.0.6.5 or later to have support for the LogMiner, and OpenVMS version 7.1 and later. There are actually some additional considerations that I'll talk about in a bit. To actually run the latest Java versions, you need something close to the latest OpenVMS version on Itanium. In the RDB database, you need to have circular journals enabled, and you need to have continuous LogMiner enabled. And those are both database administration topics that are beyond the scope of this session. You also need immutable primary keys, and I'll come back to that in a bit. But we need to know what the logical primary key is in the source database to use that to replicate data to the target database. And there are issues if your source application changes those primary key values. For this example, we're going to use the RDB sample personnel database, pretty much off the shelf. That is great for doing small examples. I create it using the SQL $sample personnel procedure, creates the database. We then add some after image journals. In this case, I'm going to reserve 20 journals, add 4 journals, after image journals, enable the server to be automatic, enable continuous LogMiner, and then alter the database. And I'm going to enable fast commit and AIJ backup for this example database. You can optionally add a set of VMS functions that we provide the script for. This allows an SQL procedure, an RDB SQL procedure, to access system services such as set symbol and get symbol, and to get dates and so on. Add this and do a show functions. This is not actually required. It's required if you want to use one of the LogMiner Loader features to exclude some tables when you do some of the configuration file generation. I mentioned immutable primary keys. In the configuration files that we're going to generate and look at here, we use the primary key to identify the rows that we're going to update in the target database. And if that changes in the source database, we only get the after image change of that, and so we can't do a one-for-one replication if you're changing the primary keys. All right, so we've got a source database that we created using the script. Now we need to create a target database. The script to create the target database can be created with the RMU extract. In this example, item equals table, index, and constraint. And I'm going to specify the language ANSI, so this matches the SQL standard as closely as possible. We then have to do some editing of the script to change some data types to match what Oracle supports, and so on. The issue with data types is that the data types in the target are not exactly identical to the data types in the RDB source database. So there are several ways to map the data types. We'll go through quickly a couple of the possibilities. And I'm going to leave this mostly for reference rather than looking at all the details. But it's useful to look at when you're actually doing this yourself with your own data. For example, if we have a varchar in RDB, then in Oracle, we're going to want to do a varchar 2, and so on. String data types are fairly straightforward. Numeric data types, the RDB data types, you would generally, in Oracle, use number data type with particular precisions. At the bottom, I've got this thing originating DB key, and I'll talk about that later, but that needs to be a 64-bit integer, which you can get in Oracle with a number data type. Date-time data types are something that you have to look at carefully. A RDB date VMS corresponds to an Oracle 23AI timestamp 2, and so on. So how do you get at the 23AI database? There's a variety of tools. Oracle SQL Developer. There's a tool called DB Visualizer that we've used a lot for accessing multiple databases. There's the SQL Plus command line interface on the target database. In this case, the examples that we're going to show use SQL Plus on the Oracle server. On the Oracle server in SQL Plus, when I attach to a database, attach to the schema that I'm working with, I can see the tables with a select table name from user tables. This differs from RDB, where you can do a show tables. In Oracle, you have to do queries of the system tables, the information tables. To see what columns are in the table, I can do a describe table. In this case, describe employees, and we see that the employee ID is not null, char 5, and so on. So what do we have to do to set up a LogMiner Loader session? We need a JDBC driver. We need to set up an options file to tell RDB what data we want out of the RMU unload/after. We need some configuration files so that we understand what the data is going to look like that we get from RMU unload/after, and how that data maps to the target database. And then we wrap all of this in a VMS command procedure. In this example, we're going to use the Oracle JDBC driver that is in OJDBC 8.jar, the latest version of it. This implements JDBC 4.2 and is certified either with JDK, Java Development Kit 8, or Java Development Kit 11. This is important because on OpenVMS, we have JDK 8, and so we have to have a driver that is compatible with that. We downloaded this from an Oracle website, the site called JDBC Downloads. Now, I download this onto my local system, which happens to be Windows, and then I need to get it to the OpenVMS system. The OpenVMS system needs to be, the disk needs to be ODS5, which allows the disk file system to support lowercase names. So I'm going to use FTP to FTP the driver of the jar file to open VMS. I then have to reset the file attributes with this set file / attribute equal command. At one point, I looked up what all these values were for the attribute and have long since forgotten it, but this is a critical string because without this set file / attribute, you won't be able to use the jar file. It won't be readable from Java on OpenVMS. Sidetrack on Java. If you're using alpha on OpenVMS, the maximum version available is Java 1.5. And the limitation there is finding JDBC drivers that will work with Java 1.5. So in this case, we're using Titanium, IPF OpenVMS 8.4-1H3. We're going to use a Java runtime environment. There are a couple of different ways to access Java. One is the Java Development Kit, which is the full development kit. You also can get Java runtime environments. And the beauty of the JRE is that you can have multiple JREs on a system. For systems such as ours, where we're doing mostly software testing, we will switch JREs to make sure that we test with versions of Java that our clients are using. But in this case, I'm going to use a recent version from VMS Software Inc., version 1.8.0.222. So this is a JRE, and do some setup to point to the appropriate directory where the JRE is installed. Okay, now we need to generate some files. To tell the RMU unload /after /continuous which tables to unload, I'm going to use the procedure JCC create LogMiner _options_file, and this will generate an options file. And this is a list of all the tables you're going to unload from the source database. If you don't want to unload every table, then you can edit the output file and comment out some lines. And I'll show an example of that in a moment. We have the capability in the procedure that generates the option file of explicitly ignoring some table names, but to do that requires that you have VMS functions installed on the source database. In this example, there is a warning because JCC set symbol is not defined, because VMS functions are not in the database. So this exclude capability is disabled. Since we're not using that in this example, that's not a big deal. So the options file looks like a list of files and an output. In this case, the output is defined by our procedure, and it's going to be, when we actually fire up the LogMiner Loader session, there's a logical name, and the logical name Rdb _LogMiner _output_ file is going to point to an OpenVMS mailbox. So this value is critical for how we work. You don't need to edit it. You don't need to worry about defining it because the procedures will define it when they run. In this example, if you look at third from the bottom, I've commented out the table resumes. So we're not going to replicate resumes to the target. The reason in this case is that the resumes table includes an Rdb type called a segmented string, and there are complications replicating segmented strings. that I can talk about at some point, but not at the moment. I then need some additional files. I need a file that describes the source data, and I'm going to a file that describes the target, how things map to the target, and this is going to implicitly create a date filter file, and I'll come back to that in a moment. So the source file describes the data that we're going to get out of the RMU unload/after. If source tables changed, if you alter a table and add a column on the source database, then this file will need to be regenerated. The target table, other than that, you shouldn't ever have to edit the table file. The target description, the map table file, you may have to edit, and I'll come back to that in a couple of slides. So what's the table file look like? For each table, there's the table name, a version number, and then a list of columns. The columns contain the column name and the data type information and other information that's related to the data type. The command procedure that we just executed extracts this information from the RDB table, RDB system table, RDB $relation_fields. And we need this information to be able to understand the data we get from the Rdb LogMiner. You don't want to generate this by hand because it's going to be difficult to get correct. That's why we wrote a command procedure to do it. The map table file contains entries for each of the tables that are going to be replicated. And so it starts off and says, I'm going to replicate the source table employees to the target table employees. In this case, these are the same. In other databases, I might have different names on the target database that for particular tables. And this is how I would say that employees replicates to some other table on the target database. And there's a comment here that says we're using the defined primary key constraint as to identify the primary key. So down at the bottom, we have this entry that says map key, which says that the key for employees is the employee ID. The primary key is employee ID. So that's what we're going to use in the replication when we go to update the target database. And in this case, that information was pulled from the fact that there's a primary key constraint on the employee source database, source table. Candidates, there wasn't actually a primary key or unique index on the source database. And so the procedure adds a virtual column that we're going to call originating DB key and uses originating DB key as the primary key. Using originating DB key can be problematic because that's actually a physical address of the source data. It may be useful in some cases, but if you don't know the primary keys of your data, then you're going to want to spend some more time with this procedure or with the configuration files. In the case of job history, there is also not a primary key or unique index in the source data. So the procedure generated the originating DB key columns. However, I've edited this file to comment out the originating DB key columns, and I've added a map key that is the combination of employee ID and the job start date. And that's because I know how this data works, and job start and employee ID uniquely identifies a record. So I had to edit that in based on my knowledge of the data because we didn't have a rule about that in the database. So the map table file often requires editing to correct the primary key, or if the table or column names are different in the target database. The map key is the logical primary key that's used when updating or inserting into the target, and it's generated based on a primary key constraint on the source or unique index on the source table. And if neither of those, it uses the originating DB key column. If you do use originating DB key, you actually have to add that column to the target database. In RDB, it's a physical address of the source record. You need an 8-byte integer, sometimes called a big int. In Oracle, it's called a number in the target DB. The risk of using originating DB key is that if you reorganize the source table, then the DB keys change, and so you have to completely reload the target table. But that's an issue we can discuss in more detail in another talk. The date filter file we added because we've found that some applications have bogus dates. The issue is that the OpenVMS data type supports dates well past the year 9999. However, the date formatting functions only support 4-digit years. So if you end up with data that's in the year 10,000, then we're going to get an error when we try to replicate that date because we're going to truncate the year. What this filter does is it basically filters out any row where the date is not between the 17th of November, 1858 and 31st of December, 9999. And we'll log that, but basically it filters out bad dates. It filters out data with bad dates. If you only wanted to filter out the date but send the row anyhow, then you could do that with some clauses we'll talk about later. So this is optional, and we're not actually going to use it in the example here, but it's useful for some environments. Okay, so we have an options file, we have a source database, a target database. We need a command procedure to put everything together. And in this case, I'm going to call the command procedure mfp_oracle23ai.com. This is my naming. It's going to need to do some things like set up the environment with JCC LML user and JCC LML JDBC user, define some logical name, and when it gets done, it invokes the JCC run CLM LML with 3 parameters, a parameter pointing to the database, a parameter pointing to the options file, and a parameter pointing to the main configuration file. In this case, I'm calling it mf_personnel_JDBC_023ai.ini. And that actually is going to include the table and the map table file we just talked about. It also is going to include information about how to connect to the target database, and I'll come back to that. So this is what it might look like. So we're defining the loader name, and this is inventively called KWH_O23AI. We're going to tell it what to do with the high water file, and I'll come back to that in a bit. It has to do with restarts. going to define a checkpoint file so I know where it is. And the checkpoint file keeps track of where we are so we can restart in the same place. I've got a logical name that points to the directory that contains AIJ backups, and that is also used for restart. So it allows us to restart not just in the AIJs that are actually live on the database, we can start in the backed up AIJs. And then the command to start up the loader, the JCC run CLM LML command. So this configuration file contains a number of things. We've got some logging commands in it. Sort by record, input is IPC, and I can go look those up. It's not important for today. Specifying the checkpoint, and what this says is that we're going to checkpoint every 25 source transactions. We're going to shut down if we have 10 consecutive failures. So if we have a failure talking to the target database, we'll retry 10 times. The target node is on Parnassus, and we're going to use port 1521, which is an Oracle default port. The Oracle schema is C ## Keith, and I'll come back to that name. And we're using that for the validation, and I didn't include my password in this example. We then specify the JDBC driver we're going to use and how to get to that driver, and so on. Down at this bottom, you see the include statements for including the table file we talked about a few slides ago and including the map table file that we just talked about. Let's look at the connection string. With the JDBC server, figuring out the connection string is, in some ways, the hardest part. You have to find it in the documentation for the particular JDBC driver. For Oracle, this is JDBC:/Oracle:/Thin. Oracle 23AI is installed on the node Parnassus, which is a Linux 9.5 VM in our network. The default port is 1521. If you've changed that in your Oracle configuration, then it has to match here. In this case, I'm using Oracle Free. So Oracle Free sets up an SID, system ID, and the tnsnames.or file on Parnassus. I could go and edit that and use something different, but I'm using the defaults in this example. Okay, sidetrack. Why did we call this server Parnassus? Well, in Greek mythology, the Oracle of Delphi is found on Mount Parnassus. And a number of years ago, when we did an older Oracle installation, I installed it on a node called Delphi because, to find the answers, we had to go to the Oracle on Delphi. Since we'd already used Delphi, I used Parnassus for this instance. End of sidetrack. The specification of the JDBC driver is found on the Oracle webpage. I mentioned that in the comments of the procedure. The JDBC class path is a VMS directory. In this case, it's a Linux-style path that is mapped to a VMS directory structure. So I have a logical device, JCC root, that has the folders keith.sqlclass.oracle.23ai, and the OJDBC jar file is in that folder. And so the class path has to map to a VMS location. And in this case, the jar file name is case sensitive. Okay, so I've put all of this together. I submit this the command procedure I built as a batch job because I really don't want to run it interactively. And this is going to set up several processes. The CTL process is the main batch job that started this, and that creates some sub-processes. The CLM sub-process is the process that reads from the source DB. Actually, it reads from the mailbox, or this is the process that runs the RMU unload/after command that writes to the mailbox. And then we have, in this case, one thread process, but it's possible in some situations to configure it so you have multiple threads that read from the source database, actually from the OpenVMS mailbox, and write to the target. So I get this running on the Oracle 23 AI. I do a query that says select asterisk from colleges, nothing selected. In the RDB session, I do an update colleges set city equals city. This is what we call a no change update because we're updating the rows, but we're setting the values to be exactly the same. But the effect in RDB is that those rows are written to the afterimage journal. When we commit, the committed transactions are extracted, passed to the LML process, which writes them to the target. And now when I do a query on the target, I get 15 rows that hadn't been there 60 seconds before. Okay, so that's just a quick demo of this configuration working. There are various log files that are created for each of the processes. There's the log file from the batch process, MFP_Oracle 23 AI, and then we set up log files for the CLM process and for each of the low LML loader thread processes. These contain logging information that's useful for understanding what happened. If you get everything working, you don't need to look at these. But when you do have an issue, you need to look for the first exception in a log, because often one exception will trigger a number of other exceptions. And if you start at the last one, then you're looking at symptoms, not at the actual problem. If you're working with the JCC LML support team, we're going to ask for those logs because we've written information to those logs to help us understand what's going on. And we have the ability to enable additional logging in some cases. Once I get an LML session running, I want to see how it's doing. And so that we have a utility, JCC LML statistics, takes a couple of parameters, the loader family, the number of refresh seconds, and the type of logging, and optionally a tardy threshold and an operator class, so that if you're more than n seconds behind production, you can send operator messages. In this case, I'm just looking at the loader session, KWH_023AI. I'm going to look at it, refresh every 5 seconds, and I want to look at the details. That's going to give me a screen that looks like this, where on the left side, it's describing the input, how many transactions, how many records, how many modifies, deletes, and commits. On the right side, it's looking at the output. In this case, we're about 4 seconds behind the input. We've sent 500,000 messages. And most recently, on the most recent checkpoint, we sent 50 messages, and we averaged about 10 per second, so about 5 seconds. And the rate was at 106%. And so we're catching up. We'll look a little more at the bottom right in a moment. So we've done a bunch of things and output the data. In the bottom right corner of the display, we have details about where we're spending our time. In this case, the rate was 106%. We're spending a lot of the time in input in this example and not much of the time in output. So we're about 0.9 seconds behind from CLM. The LML session is about 5.3 seconds behind CLM. And 99% of the time is actually waiting for input. 0.3% is converting, 0.7% is waiting for the target. So this is actually pretty close to real time. When you're looking at the performance, and you look at this, if you see that you're spending 80%, 90% of your time waiting for the target, that means you have to look at the target database to see what the performance issue is, because this is a database update connection to the target database. And so if there are performance problems here, it's going to be because there's some performance bottleneck on the target database. Okay, so we got a session, but what about shut down and restart and adding additional information and filtering and transforming and multiple update threads and verifying the target, and what other targets can we get to? We have a command to shut down the loader session. This does a clean shutdown. It doesn't operate immediately because it waits until the LML process catches up and reads everything that it's been written to the mailbox. On restart, we use the checkpoint. In the case of an RDB target or an Oracle OCI target, we use a high water table in the database. In the case of JDBC, instead of putting a table in the target database, we create a file on the local system, a checkpoint file. What this allows us to do is to restart at the point of the failure. Now, it's possible for various reasons that a restart may resend some transactions. And so you need to understand that when you're designing the target database. But it's better to resend transactions than to miss transactions. We can look at the restart information with JCC LML dump checkpoint command. So in this example, do a dump checkpoint of the checkpoint file name. And it says that the write timestamp was at 2108. The loader name, the completion flag, which we don't really use much, the checkpoint interval, the input data source, which is the LML session, the start time and commit time, the transaction sequence number, which is an internal RDB transaction sequence, the loader sequence number, which is something that we keep track of. The AERCP is a value that we get from the RMU unload/after command. And on a restart, we send that to the RMU unload/after, and that tells it what where to start in the after image journals. So the 5 fields, there's a version number and some other version number. The 101 is an RDB AIJ sequence number. The 2102 is a virtual block number. And then the last 2 numbers are transaction sequence numbers. But this is constructed in such a way that we write the checkpoint only after the data has been committed on the target database, which allows us to restart at the correct point. We can add additional information. I mentioned originating DB key earlier. We can add loader sequence number, the transaction start time, the transaction commit time, the process ID of the source OpenVMS transaction. That's the process ID of the process that updated the RDB database, and a number of other things. We also can create a virtual table, and this could be one of several things. If you want to do some transformations on the replication, you could create a virtual table in the target that is based on several tables in the source database. You could create a virtual table in the target that contains commit records. For every time the source database commits, we get a commit record, and we can map those to a target table. And so you could have information about each transaction committed on the source database at the transaction level. We also can filter data. I showed you the filter map on dates earlier. But you can do other things. When we started looking at how to add filter capabilities, we decided that RDB has really nice syntax, SQL syntax for doing filtering criteria and doing predicates, and we could just use that. So everything that you see here is RDB SQL. And essentially we process it using dynamic SQL and the filter map database. So this can only look at the current row, it can't look at other rows. I mentioned the filter map database. We set this up specifically for evaluating filters. There's not really much data in it, but we attached to it and used dynamic SQL to evaluate the filter expressions and see whether it's true or not. By default, this is created using the logical name JCC LogMiner Loader filter dir and filter name. This is all has defaults and will be automatically created. So you only need to worry about this is if you need to put the filtering someplace else other than the default. The database has some specific characteristics, and occasionally we've run into cases where for a particular environment, the defaults aren't sufficient. And so you would use an example such as this to create the database. You can do some transformations using the filter map database. You can map multiple source tables to one target table, one source table to multiple targets. You can turn nulls into values or values into nulls. You could even add a function to the filter map database. We have a talk that talks about this, something called data transformations using the JCC LogMiner Loader map result. So I'm not going to talk about it here. You can do multiple update threads. So parallel 1 to 4 says we're going to have a minimum of 1 thread, a maximum of 4 threads that are updating the target database in parallel. And the shutdown and startup say that if we're delayed more than 10 seconds, we'll start up a new thread. If a thread is inactive for more than 30 seconds, then it'll go ahead and shut down. When you're tweaking these parameters, you need to understand the effect on the target database, because sometimes doing more work in parallel is good, And sometimes it just means that you have more congestion on the target database. So it depends on a lot on your transaction mix, and there's not one answer that fits everything. Okay, so I put all of this data into a target database. How do I validate that the data is the same? Some of the challenges are data type representations, things like trailing spaces and character sets, floating points representations, because when you convert, say, a G float to an IEEE float, the precision, the fractional precision may change. How many rows determines how long it takes to actually validate. To really compare, you have to freeze updates. And you can do this on the development database, but probably not in a production database. For our loader regression testing, what we do is we set up a loader session. We do random updates for a while on the source database, and then we freeze updates. When everything catches up, we copy the target data to parallel data in the source tables in the source database, and then use SQL queries to compare the data. So that works in a test environment. It doesn't work in a production environment. So there is a challenge in validating to yourself that the data that exists, that's been replicated to the target, does actually match the data in the source database. And we can spend some time working with you if you have more questions on that. Okay, so we get this data into an Oracle 23 AI database. And there's actually some interesting things that you can do in Oracle 23 AI. Oracle 23 AI implements a new standard that was completed in 2023, something that is called SQL PGQ. In addition to working as doing RDB databases, database performance, I also participate in the international standards process for the database languages in the SQL standard. And so I think this implementation is really cool because I spent a couple years helping to write the SQL PGQ standard. What PGQ actually does is define two capabilities. The first one is to create property graph views of an SQL table. The second is to allow you to do property graph queries in the SQL from clause. And I'll show you a quick example of these. So it gives you the power of property graphs on SQL data. So create a property graph view. In this case, I'm going to map the vertex tables, which in my short example are going to be the employees table and the jobs table. And to connect those, we have the edge table, which is job history. And if you've worked with the RDB employees database, there's an employee ID in job history that allows you to connect to employees. In job history, there is a job code that allows you to connect between job history and the jobs table. And so that is essentially what this is doing, is defining a view that includes those connections. The job history is an edge where it references the employee ID and employees, and the job code in the jobs table. This is a small example, so it doesn't show you the full power of property graphs, but this gives you an idea of where to start. So I've created this, And then in my SQL query, I'm going to include a match statement that specifies a graph pattern. And this is a simple example where we know that there's this thing called job history in the relationship. In a larger example, larger database, what this would allow me to do is to do queries and find employees and that are connected to other tables without knowing anything about the connection. But in this case, I've got a query, a match query. I'm going to look at it only where job end is null, and I'm going to return the columns. And so this is doing a property graph query and then returning just the columns to the source SQL. Creating the property graph views requires understanding the data because you need to know what the relationships are. The SQL allows you to build queries and build complex relationships into the query, but in the where clause, you have to understand the relationship between all the tables in the from clause. What this is doing is in the property graph view, you're describing the relationships between the different tables, and then in the query, you don't have to know what that relationship is. So there's some, I think, some cool capabilities, but the details are beyond the scope of this presentation. So what else do we have? RDB targets are relatively straightforward. Setting up a LogMiner Loader session requires a bit of fiddling. What we found is that when working with clients, we do some amount of support during the initial setup. Once things are running, you don't have to touch it. So RDB targets are pretty straightforward. Oracle targets require installing the Oracle call interface, the Oracle client on OpenVMS. The last version of the Oracle client on OpenVMS is, I believe, 11G. And you have to understand some data type differences. JDBC targets require a few more steps because you have to have Java on your OpenVMS system. And then you have to find the appropriate JDBC drivers, copy them or FTP them to OpenVMS, and then reset the file characteristics, specify the class path, specify the connection string, and understand what the data type differences are. We also support a number of other things, including Kafka. I've got a link to a talk we did a while back on Kafka and replicating data to publishing committed data to Kafka. So, replicating data Oracle 23 AI is just another JDBC target. So if you've set up replications, it's not particularly hard. One of the reasons for the details in presentations like this is so I have something to copy the next time I need to do it. In this case, we are using Java 8.0.222 something and Itanium VMS. We will be able to do this also on x86 VMS when RDB is actually available there. And as I said in the last couple of slides, Oracle 23 AI supports some interesting capabilities for doing property graph queries on the SQL tables. So that's all there is to setting up a session. If you want to learn more, we've got some websites about the LogMiner Loader. We have a variety of documentation. We have a variety of blogs where we're talking about different capabilities and a number of sessions that we've done over the years. If you want to contact us, the email is info@jcc.com. And if you're an RDB user, we do have an RDB mailing list email reflector that you can subscribe to. And that's it for today. Let us know if you have questions.